Mhm. Let's see. All right, so we're going to be starting. Just give me 1 second. All right. So welcome everyone to week 5 of Combinatorics, or which is talking about more sets and partitions. So sets and partitions are something that are actually really important in my opinion. So pretty much so for sets and partitions, we need to like they show up in early AMC8, late AMC8. They show up in early AMC10, late AMC10, and even past that, they can show up at like IMO level. So I really hope that you guys actually pay attention this time, because sets and partitions, day 2, this is going to be an interesting class, guys. So yeah. And wait, just give me a second to launch this poll that is not working for some reason. Relaunch polling. Wait. Sorry, give me a sec. Let's see. How do I? Wait, how do I? Wait, is this? Okay, that did not work. Wait, oh, here we go. Okay. Anyways, so now we're going to be moving on into our theory for today. So first, what is a partition? So a partition is a partition of a positive integer n is the expression of n as one or more positive integer or parts, as people like to call them. And the order of the integers in the sum does not matter. So for example, if we're partitioning 3, then 1 plus 2 would be the same as 2 plus 1. So make sure you guys count those as the same partition and not as different partitions. Anyways, so, and a lot of times people like to represent partitions of n as p of n. So for example, in this case, for this example problem, they would like to call it p of 6. And if you guys want some examples for what partitions look like, here are some examples of what the partitions of 1, 2, 3, 4, 5, and 6, and 7 are, with the partitions of one of them mischievously removed for no reason. So yeah, let's quickly move into example 1, which is how many different ways are there to partition the positive integer 6? So let's see. So if we want to partition 6, we can do this in an organized casework sort of manner. So first we see how many ways there are if we just do it into one part. If we put 6 into one part, we can just do it as 6. Now, let's see how many ways we can do it into 2 parts. We can do it as 5 plus 1, 4 plus 2, or 3 plus 3. And note that the reason we don't count 2 plus 4 or 1 plus 5 is because ordering does not matter. And we don't count things like 6 plus 0 because it's the expression of n as one or more positive integers. Now let's keep going and see how many ways there are for 3. So for 3 parts, we can represent it as 4 plus 1 plus 1, 3 plus 2 plus 1, or 2 plus 2 plus 2. So this is for 3 parts. And now we move on to 4 parts, which is 3 plus 1 plus 1 plus 1, 2 plus 2 plus 1 plus 1 plus 1. Oh, sorry, 2 plus 2 plus 1 plus 1. And then after that, we keep going to get the last few are 2 plus 1 plus 1 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. Yeah, plus a lot of other ones. So now, to find the answer to this example, and sorry for my diagonal writing, all you have to do is count the number of total partitions we have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So in total, we have 11 partitions. And now you might be wondering, is there a better way for us to do this without casework? Because doing casework is really annoying, as Alice just seemed to ask. And unless you guys are like fans of like weird stuff like linear algebra or something, and even the linear algebra solutions are very bad, then the fastest way is actually just going to be doing casework, because currently partitions are like an open part of math. Like a lot of people are trying to perform research on them and try to get like a closed form for partitions, find different sorts of ways to easily calculate partitions. But unfortunately, we in the math community have not been able to find that much about it. So for now, we're just going to have to unfortunately count the number of partitions. And yeah, there aren't exactly that many nice properties about them. However, they do occasionally appear in math. and like AMC8, AMC10. So just make sure that you know what they are and know how to do the casework to count the number of them. So yeah, those are partitions. And now we're going to be moving on to the next one, which is compositions. So compositions are similar to partitions, except for the fact that when we put them into one or more positive integers or parts, order does matter. So for example, if we're partitioning 3, then the partitions 1 plus 2 and 2 plus 1 are distinct. So in other words, we would count this as 1 and then 2. So this is pretty interesting. And since, as we know, partition for P, composition for C, we normally represent compositions as C of n. So for example, let's say that we want to find the number of compositions of 3. Well, we can do this as 1 plus 1 plus 1. We can do this 1 plus 1 plus 1, 1 plus 2, 2 plus 1, or 3, which is equal to 4. And if we wanted to find the number of compositions of, say, 2, it would just be 1 plus 1 and 2. And you might notice a suspicious little pattern going on here. If we want to find the number of ways to compose 1, it's just 1. So there's 1 total way. And if you look at these, not sure if you guys noticed any sort of suspicious thing going on. And I'll give you a hint. If you want to find C of 4, that's equal to 8. So yeah. And as a result, if you guys noticed a suspicious pattern, which was just multiplying by 2, for our first example, we're going to be proving that the number of compositions of n is just equal to 2 to the n minus 1. All right, so if you guys want to see, here's how we do this. So we're going to be doing something called induction, I think. And I'm not sure you guys knows what induction is, but I'm just going to quickly go through it without explaining too much detail because I know that it's kind of confusing. So we can see that the pattern follows for the first few values, right? So we can see C of 3 is equal to 2 squared, C of 2 is equal to 2 to the 1, and C of 1 is equal to 2 to the 0. So now let's say that we want to find C of n. Now note that since order does matter, then what the value of the first term does actually matter. So for example, if the first term is a 1, then we just have 1 plus other stuff, right? And in this other stuff, we know that this other stuff must sum to n minus 1. So as a result, the number of compositions here will just be C of n minus 1. Now similarly, if the first term is a 2, then we have to have some other stuff here, which is equal to n minus 2. So as a result, the number of ways to sum this n minus 2 stuff is just C of n minus 2. And so on, all the way until we get to just C of 1. No, 0 does not count. So for example, if we wanted 3, then 3 plus 0 would not be a composition that you could do. However, if we note that since if we assume that all of the previous ones follow the pattern, then we can see that, and also at the end, in case we just do 1, we have to add in 1 because this is just if we do n. So for example, here would be n minus 1 plus 1, and then this is just if we put down n. So now from here, if we assume that all of these follow the pattern, then we know that C of n minus 1 is equal to 2 to the n minus 2. This is equal to 2 to the n minus 1. N minus 3. All the way up to 2 to the 0 plus 1. And now if we notice, this is just a very simple pattern, classic pattern, and we can see that this is equal to 2 to the n minus 1. So this is how we prove that C of n is equal to 2 to the n minus 1. And this is actually a simpler version of what is called induction, but I don't want to be, I think I said this before, but I don't want to be going into too much detail just to make sure you guys aren't too confused. So just know if you guys ever want to find the number of compositions of a positive integer n, then the number of that is just 2 to the n minus 1. So this is pretty useful and actually does show up in quite a few problems. So now we're going to be moving on to example 3, which is find C of 3 plus C of 4 all the way up to C of 12. And you know, I'm going to be a bit discreet here, but this thing right here might be a bit helpful when trying to find the answer to this problem. So I'll give you guys some time to think about it, like 10 seconds, just to make sure it really clicks in your brain. What is a composition? All right, I'm really bad at counting, so hopefully 10 seconds is actually up, but if it isn't, then oops. So yeah. So if we want to find the value of C3 plus C4 all the way up to C12, then this is what we want to do. So we can see that this is if we use the formula from example 2, we can see that this is equal to 2 squared plus 2 cubed plus 2 to the 4th all the way up to 2 to the 11th. And the way we got this was just by repeatedly applying C of n is equal to 2 to the n minus 1. So now what we can do to make this more interesting is we can factor out a 2 squared to get 2 squared times 1 plus 2 plus 3 all the way up to 2 to the 9. And now that we have this, oh, sorry, this is a 4. This is a 2 squared, sorry, my bad, guys. But now that we have this, we realize that using one of the formulas, we can get that this is also equal to 2 squared times 2 to the 10 minus 1. Woohoo! And now from here, since we've actually memorized what 2 to the 10 is, right, guys? We've all memorized what 2 to the 10 is. We know that this is equal to 4 times 1023, which is equal to 4092. Woohoo! And hopefully that made sense. So you guys, if you guys have any questions, feel free to ask. And yeah, we'll wait about 30 seconds to see if anyone has any questions. Any questions, feel free to ask. We don't bite, so yeah, feel free to ask. Oh, don't worry, I can bite through cameras. All right, anyways, now we're going to be moving on to this next quick stuff. So if you guys were worried that we weren't going to talk about sets at all today, well, fear not, because the rest of today is probably mostly going to be about sets, because sets are important. So I wanted to make sure we had a day 2 about them, which would be today. So first of all, we're going to quickly cover some common notation. So by the way, you guys might see these from time to time, and people like to do these. So I just wanted to make sure you guys were knowledgeable about them. And also, for some reason, my latex was not working. So these are actually not like technically correct, but they're close enough. For example, technically the set of all integers would be something like this. Something that looks like this. And the set of all complex numbers would be something that looks like this. But it's close enough. Anyways, we're going to quickly list these out. So for example, Z is the set of all integers. Q is the set of all rational numbers. Oh, whoops. I think I seem to have deleted one, but N is the set of all natural numbers. Q is the set of all rational numbers. A is the set of all algebraic numbers. So algebraic numbers are just like polynomials. So for example, 3x squared plus 5x plus 6. Rational numbers are just say 5 over 6, any number that can be represented in a fraction. Integers are any whole number, and natural numbers are integers, but only the positive ones. Now next, R is the set of all real numbers. So this is pretty much any number you can think of, like root 6, pi, e, all this crazy stuff. C is the set of all complex numbers. So this is just a set of all numbers that can be expressed as a plus bi, where I is equal to the square root of -1. And hopefully we all have heard of these strange new imaginary numbers. And imaginary numbers, you might think that these are the same as complex numbers, but they aren't, because imaginary numbers are just numbers that do not have this real part. They can be expressed as like x times I. And last, S is the set of all Sedenians. And I honestly have no idea what this is, but I just had to include this in here so I could have a good acronym. Anyways, here's my very good acronym that hopefully includes all of the above letters. So it's Zesty Rich can quickly neutralize Isabella and Stephanie. So yeah. So for example, and just to make sure you guys actually have the gist of it, if we say let the set, for example, if we say the number x is inside the set of z, this means that x is an integer. Okay. What are Sedenians? I have no idea. All right. Anyways, we're going to be quickly moving on to example 4, which is how many elements are in the intersection of the set of natural numbers and the set of imaginary numbers. So if you guys have any guesses, feel free to say them in the chat. I'll give you guys some time to count. All right, yes, good job. It is actually 0 because as we can see, the set of all natural numbers is like 1, 2, 3. But then the set of all imaginary numbers is things like I, 3i. So there are actually no sets in common here. So this is equal to 0. Now, example 5. How many elements are in the intersection of R, or the set of all real numbers, and Z, the set of all integers? So again, I'll give you guys some time to make sure, you guys have some time to try out this quick example. And yes, that's correct. The answer is actually infinity because as we can see, any integer is a real number. So as a result, there are an infinite number of elements that are in the intersection of Z and R. So good job, guys. All right, so that's all the theory for today. So now to make sure that it all really sticks in your head, we're going to quickly be moving on to some introductory problems. So this is the first question, and I'll give you guys some time to read it because it's a pretty long question. So and yeah, I like creating I really like to create long introductory problems. So yeah. I see you, Kevin. Oh shoot, I can't draw this robot. Oh, here we go. Woohoo. I'll give you guys a couple more seconds to read the problem. How does one have a negative FTW rating? By being too good. Woohoo. All right, so now that, let's see. For the Win is like this online AOPS game where you answer math questions as fast as possible. And yeah, you have a rating that determines how good you are. All right, anyways, so now that hopefully you guys have had some time to think about the problem and you guys have read the problem, we're going to be quickly solving this to make sure that Rich can beat Andy. And Rich is not playing FTW right now, in case you guys are wondering. So anyways, so the question is, how many ways are there to partition the number 8 without using the number 1? And and unfortunately, as I told you before, there aren't exactly very many good ways to find the number of partitions of a number without just doing straight casework. So we're just going to have to straight casework bash this. So let's see. If we want to partition the number 8. So first of all, let's find the number of ways there are to express it as one term, which is just 8. Next, we find the number of ways to do 2 terms. We would normally start with 7 plus 1, but since we can't use the number 1 because it's banned, we're going to start with 6 plus 2, 5 plus 3, and then 4 plus 4. Oh yeah, Andy already got the problem actually, so it doesn't really matter anymore, but we're going to solve it anyways because Andy's a robot. So now we're next going to put it into three ways. So if we're going to be partitioning it into 3 parts, we can do it as 4 plus 2 plus 2 and 3 plus 3 plus 2. Because note again that we cannot use ones, which makes the casework a bit simpler. Next, we go on to 4 parts. And if we're using 4 parts, there's actually only one way to do it, which is 2 plus 2 plus 2 plus 2. So as a result, counting up the total number of partitions, there's 1, 2, 3, 4, 5, 6, 7. So there's 7 partitions in total of 8 without using the number 1. So if you guys have any questions, you can ask in the chat. Let's see. Did Rich lose? I won't answer that question because I don't feel good right now. What if the number was 1,000? Well, they probably wouldn't ask you that question. So for reference, there was this Who Wants to Be a Mathematician question, which asked how many ways are there to partition the number 1,000? And it's actually an estimation problem because no one actually knows the number of ways to partition the number 1,000. So if it asked you for 1,000, I think you could pray and use the cloudy method. But other than that, there's not really any good way to solve the number of partitions of 1,000. Does Andy have an off switch? I think so, although I have yet to find one. All right. Who is the best of you out of FTW? Obviously me, right? Okay, anyways, so now we're going to be moving on to the next problem. And again, since it's long, I'll give you guys some time to read it. And I'll be tracing this game controller while you guys read this problem, in case some of you are bored and want to watch my excellent tracing skills. But in the meantime, feel free to read the problem, think about it, try out some cool stuff, realize that combo is an awesome subject, I'm sure all of you guys love combo just as much as me, right? Woohoo. Video games. All right, I'll give you guys a couple more seconds to read the problem and think some deep thoughts. Think about the meaning of life if you're done, the usual. All right, so now that you guys have hopefully all read the problem, we're going to be quickly going over it. So since Stephanie is currently under trial, and we can see that the Council of Riches has decided that she has 4 different options. She can either be binded to George Washington's face, she can be dropped onto the peak of Mount Everest, take away her Fortnite privileges, or let her go free. However, it is also noted that none of the riches chooses the last option, so we can pretty much just ignore this option. So how many ways are there for the riches to choose between the options? And also note that all of the riches are identical. So for example, if rich 1 chose option A and then rich 2 chose option B, that would be the same as rich 1 choosing option B and rich B choosing option 2. Anyways, so now again, this is another partition problem, except this time we have a set size. We want to find the number of partitions of 9 that have a size of 3. And unfortunately, we're just going to have, there's actually a good way to do this with stars and bars, but we're going to be quick. The first thing we're going to be showing is just going to be straight out casework bashing, because that's what most partition problems are going to be like. So if we want 9 and we want to partition it into 3 parts, we can do this as either, and note that this time ordered, okay. So we can do this as either 1 plus 7, 1 plus 2 plus 6, 1 plus 3 plus 5. And yes, I'm just straight up casework bashing, so nothing special really going on here. But unfortunately, casework bashing is a part of life. So we're going to have to learn about it. So now there's 2 plus 2 plus 5, 2 plus 3 plus 4, 3 plus 3 plus 3. And I believe that this should be all the options. However, the reason this one is special is because each of these options are distinct. So as a result, there are ways to order them. So for example, if 6 people choose taking away Stephanie's Fortnite privileges, that's different from 6 people choosing to bind her to George Washington's face on Mount Rushmore. So anyways, so so for the first case, we can see that there's 3 possibilities. Here there are 6 possibilities, 6 possibilities, 3 possibilities, 3 possibilities, 6 possibilities, and lastly, 1 possibility. So then adding all of these up, we get 15 plus 12 plus 1 is equal to 28. Woohoo! So this is our final answer. And also, don't try to sue me. All right, so if you have any questions, feel free to ask. There's a good solution. If you want me to show that, just ask. Although if you want to move on to the next problem, then don't ask. So yeah. And if you can ask in the Q&A, you can ask in the chat box, anything. Yo, you want to show the good solution? Okay. So the good solution is using a more advanced technique that we'll go over probably in a later Flash Math class called stars and bars. So don't worry if you don't understand this, because this is a fairly advanced technique. So for example, since there are 3 different options, then there are we use 2 different bars to distinguish this. And we also have 9 stars, 1 for each of the riches. And then, so the number of stars in each of these 3 boxes represents how many people vote for each of the options. So as a result, the number of ways to do this is just, it should be 11 choose 2, I think. No, sorry, 13 choose 2. Wait, did I count wrong? Okay, wait, hang on. There are 9 of us, right? Wait, 3. Oh, wait, hang on, wait. Oh, sorry, wait, I don't think there's a good solution, actually, my bad. I forgot that it has to be ordered. Okay, yeah, never mind. There is no good solution. The world is a lie. Yeah, so sorry. I don't think there's a very good solution. Anyways, how do you get 6, 3, and 1? So pretty much the reason that we can have 6, 3, and 1. So if we look at this 1, so for example, voting 3 for the first option, 3 for the second option, 3 for the third option. There's no ways to arrange this. However, if we look at something like 2, 3, 4, then we can have either 2 people voting for the first, 3 people voting for the second, and 4 people voting for the third. Or we can have this ordering or this ordering, and so on. And there's 3 factorial total ways to order this, which we get 6. So yeah, it's just ordering. And any other questions? If not, we will be moving on to the next question, which is about FTW. So yes. Wait, all have to be greater than 0, so 8 choose 2. All right, so now we're going to be showing the FTW problem, and I'll give you guys some time to read this, as usual, to think about it, make sure it comprehends in your brain. Yeah. Oh, and by the way, there was actually a good solution to the previous problem. I think someone mentioned it in the Q&A, but I butchered the good solution. So if you really want, you can go to the question asking website after class and ask me about it if you really, really want to know. But I'm not going to be covering it because I'm too embarrassed right now. Yes, there is actually a good stars and bars solution. I might go over it later. If you really want to know, you can ask me in the Q&A. I mean, in the Flashmath class questions website after class. All right. And after I'm done tracing this boy, we'll continue the problem. In the meantime, you should be reading the problem and trying to think of some interesting solutions that you might think of, comprehending everything that's going on, and thinking of what you might say in the chat box. All right, now that I'm done, all right. So now that I'm done tracing this brilliant man, we're going to be quickly continuing this problem. So we can see that the set S contains all the partitions of 4, and the set P contains all the partitions of 5, as we can see here. So, however, Meanhead Andy, or Robot Andy, decides to come along and mix the elements of each set up. So for example, we now no longer know which partition belongs to which set. So if we choose 2 random partitions from the pile and place them in set P, what is the probability that both of them did, in fact, originally belong to set P? So the first step to doing this is to just list out all the partitions of 4 and 5. And I'll just save you the hassle of having to go through all this casework bash and list them out right here. And note that since these are partitions, the ordering does not matter. So these are all the partitions of 4. And for 5, there's slightly more. But luckily, since it's a small number, there still are not that many. So still fairly doable. You know, the usual listing out every single number. So now that we're done writing out all the partitions, we can count up the number. So we can see that in total, there are 1, 2, 3, 4, 5 in the set of partitions of 4. And there are 1, 2, 3, 4, 5, 6, 7 total in the number of partitions of 5. So after Meanhead Andy mixes them up, we know that they're in total 12 in the pile. So what we're trying to find is the equivalent of how many different ways are there to choose 2 partitions such that both belong to set P. So since set P has 7 total partitions, there are 7 choose 2 total ways to choose 2 partitions that belong to it. And in total, there are 12 choose 2 ways to choose 2 partitions from the pile. So in conclusion, this is our final answer. And if we want to calculate this out more thoroughly, we can get that this is equal to 21 over 66, which is equal to 7 over 22. So this is our final answer. Not that hard, despite the very long problem statement. So if you have any questions, feel free to ask. Am I using a stylus? Yes. This is my stylus. It's very cool. No one saw that. That was I think one of the wind gods was manipulating the wind, so I dropped it. I didn't do anything, so don't yell at me, please. All right, so since it doesn't look like anyone has any other questions, we're going to be moving on to this week's problem set. So this is the first problem, and I actually really, really like this problem. Although I'm not sure about its difficulty level, but I do really like it. So hopefully you guys enjoy it as well. So let P of n be the number of partitions of a number n. If P of 20 is equal to 627, P of 19 is equal to 490, then how many partitions of 20 are there that do not contain any parts of 1? So I'll give you guys about 10 seconds to think about it while I quickly explain some stuff. So as you can see, I very nicely gave you the number of partitions of 20 and the number of partitions of 19 because I knew that you guys did not want to have to write out every single partition. Yeah, writing out every single partition is very painful, especially when there are 627 of them and there are 490 of them. So yeah. Anyways, so now that we're all done, hopefully thinking about the problem, I'm going to quickly explain the solution. So the strange thing is we want to find the number of partitions of 20 that do not contain any parts that are equal to 1. So for example, an example of this partition could be, say, 14 plus 4 plus 2, as this does not contain any total ones. However, we also want to really make use of this fact because, I mean, they probably gave this to us for a reason, right? But anyways, this is actually a really slick problem and I really like its solution, so I'm going to quickly show you. So I claim that the answer is just P of 20 minus P of 19, which is equal to 137. And I'm going to quickly prove that. So we're going to actually do complementary counting. So let's first find the number of ways. Let's first find the number of partitions of 20 that do contain a 1. So this is the number of partitions that do contain a 1 in it. Do contain 1. So let's look, right? So for example, if we have a partition that contains a 1, like 15 plus 2 plus 2 plus 1, then one interesting thing we might be able to notice is that if we remove the 1, we get a partition of 19. For example, if we have 14 plus 3 plus 2 plus 1, removing the 1, again, gives us a partition of 19. And the interesting thing we realize is if we remove the 1 from all the partitions that contain 1, we can get a different partition of 19. So as a result, we can see that the number of partitions that do contain a 1 is actually just equal to the number of partitions of 19. And this is actually a pretty big brain blower thing. So if you have any questions at this point, feel free to ask. Anyone have any questions? I know that this is a pretty strange thing, and I went through it kind of fast. So if you want to ask, then you should definitely feel free. Let's see. Can I repeat it? Yeah, sure. Let's see. So let P of, okay, so for example, we want to count by doing complementary counting the number of partitions that do contain a 1 that sum to 20. Number of partitions, this should say of 20. So for example, let's say that we have something like let's say that we have a partition like 18 plus 1 plus 1. Excuse me. In this case, we can see that by removing the last 1, we can create a new partition of 19. And if we have something like 16 plus 2 plus 1 plus 1, then by removing the 1, we still create a new partition of 19. And as a result, we can see that the number of partitions of 20 that don't contain 1 is just equal to the number of partitions of 19. And the reason that we don't have to subtract the number of partitions of 19 that contain a 1 is because we're only subtracting the last 1, so it doesn't really matter either way. All right, I hope that cleared up any conceptions you guys had. Anyone have any? So from here, all you have to do is complementary counting to get the number that do not contain a 1, which is P of 20 minus P of 19 is equal to 137. So any other questions? How long does it take you to write an introductory problem? Takes me quite a while, although I won't be specifying for various reasons. Personal reasons. Makes me feel better about myself. No open questions. All right, so if you have any questions, feel free to ask. Even if you don't understand one of my explanations, that's perfectly fine. I can re-explain it again. All right, so hopefully now that you guys are all, hopefully since it doesn't look like you guys have any questions, we're going to be quickly moving on to the next problem. All right. And I'll just give you guys some time to read this problem. It's about a set containing another set, so yes. I hope you guys like the cow. It took me a while to find, but it's a pretty good picture, and I just wanted to share it with you guys, even though I'm going to be honest here, it has no relation at all to the problem. Why do I like that picture so much? Oh, I just like it. All right. I don't know. I just seem to have a special connection with it, you know? All right. Anyways, so now that you guys have hopefully read the problem, I think I say that word a lot, we're going to be quickly continuing. So one thing you guys might think of doing is just doing a long bashy casework, but unfortunately, this actually is really hard, especially considering the fact that there are 2013 elements. So as a result, doing a bashy casework would take a really, really long time. However, luckily, there is actually a very, very slick solution, or a cheap solution, interesting solution, whatever you guys like to say, that can make the problem a whole lot easier. So this is how we do it. So what we're going to be doing is considering each of the elements separately. So we're going to be considering how many ways there are to place the element 1, how many ways there are to place the element 2, all the way up to how many ways there are to place the element 2013. So for example, let's look at element 1. We know that by this condition over here that 1 must be in at least one of the sets. So 1 must be in at least one of A, B, and C. Right? However, we also know that any element in A must also be an element in B. So this is how we do this. So for example, if we say that we have 1, so now all we have to do is count the number of ways to put the element 1 into different sets. So if we call this set A, set B, and set C, the number of ways that 1 can go in it are we can say that it's in set A, in set B, in set C, in set A, out of set, in set B, in set A, in set B, out of set C, in set A, out of set B, and in set C, in set A, out of set B, out of set C, out of set A, in set B, in set C, out of set A, in set B, and out of set C, or out of set A, out of set B, and inside of set C. So as we can see here, there are 7 different possibilities. However, we also know that we have to consider this condition right here, which shows that every element inside of A must also be an element inside of B. So as a result, if an element is inside of set A, but not in set B, then that case cannot work. So as we can see, this case does not work for that reason, and this case also does not work for that reason. So instead of 7, we now have a total of 5 cases. So as we can see, one can either be for this case, this case, this case, this case, or this case. However, we also see that this thing is not special to 1. For example, we can do the same with element 2, element 3, and so on. So in other words, every single element has the same number of choices as the element 1. And since element 1 just has 5 choices, in total, there are 5 to the 2013 total ways that we can satisfy all of the conditions that are given in the problem. And if anyone wants to expand this, you're welcome to, but I'm not going to be writing that down. So does anyone have any questions? Yeah, you can't go out, 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 because at least one of them has to be in at least one of set A, B, and C. All right. All right. So it does not look like there are any other questions. So we're going to be moving on. Oh, Q&A. Oops. Excuse me. Oh, what is U? Oh, U just basically means that U is the union of 2 sets. I covered this in last class. So it pretty much means that the element. So for example, the union of the sets 1, 2, 3, the union of these 2 sets would just be 1, 2, 3, 4, 5. So pretty much it's just any element that is contained in any one of these sets. When can we learn quadratics? That is in algebra. So that's Isabella's class tomorrow. I don't know if she's covering quadratics, but yeah. Anyways, so now since it doesn't look like anyone has any other questions, we're going to be moving on to 999 Russian dolls walk into a bar. And the reason I think that this makes sense is because each of these sets contains another set. So it's the same as having 999 Russian dolls, each containing the other. So while you guys read this problem and think about ways to do it, I'm going to be drawing my very good Russian dolls. So here. Oh, Russian dolls are like these things where one of them is bigger than the other one, so it can cover that, and then the next one's bigger than that one, so it can cover that. And yeah, a quick Google search should suffice. It should show you everything about them. But if you want a picture, this is what they kind of look like. I think they were just popularized in Russia, which is kind of why they're called Russian dolls. All right, anyways, so now that hopefully you guys have had some time to look at everything, we're going to be quickly going over how to do this. So looking at this, so looking at this, we might actually get the idea of doing the same thing as what we did before. Because the previous problem had different types of sets intersecting, and it also wanted sets that contained inside of a total box thing. So as with the previous problem, we get the intuition or the idea to just look at each element individually. So for example, we look at element 1 individually, element 2 individually, and so on. So for clarity, let's just say that we look at element 1. So if we look at element 1, we can see that element 1 can either, so the way we're going to be doing this is let's look at the first set that it is included in. So for example, if the element 1 is included in the set 999, then because of this chain right here, we know that it must also be included in the set 1, set 2, all the way to set 998. So if it's in set 999, must be in S998 all the way to set 1. However, let's say that this is not true. If it's in set 998, it must be in set 997, 996, all the way up to set 1. And we can see that this pattern holds. So for example, we can say if it's in set 2, then the element must also be in set 1. And then set 1 is just sad. And then, or it also has the possibility of being in no set. So this is the set that the element first appears in. So set that element first appears in. And I'm sorry for my bad handwriting, guys. So as a result, we can see that every single element can either choose between first appearing in the set 999, first appearing in the set 998, all the way to first appearing in the set, all the way to appearing in no set at all. So as a result, each of the 999 elements has 1,000 choices because it can choose one of these options. So in total, there's 1,000 to the 999 total ways to do this because we have 999 total elements and each element has 1,000 choices. All right, so if anyone has any questions, feel free to ask. Oh, shoot. Oh, I did it reversed. Oops. Wait. Feel free to ask any questions. We don't bite. Although I sometimes do, but we won't talk about that. Oh, shoot. And actually, I did make a small mistake here. So although the logic still holds, this is I actually messed up the order of these sets. So if it's in set 1, then it must also be in sets 999 through set 2. If it's in set 2, it must also be in sets 999 through set 3, and so on. So if it's in, and lastly, if it's in set 998, it must also be in set 999. If it is, and lastly, it can just be in set 999, or it can be a no set at all. So yeah. Why do they have 1,000 choices? Okay. So I'll quickly re-explain that. Let's see. Give me a second. So pretty much, let's say that for a certain element, this is the set that the element first appears in. So let's say, so obviously the element has a choice of not appearing in a set at all. So no set. However, if it appears first in set 1, then because of this condition right here, we can see that it must also be contained in set 2, set 3, all the way up to set 999. If it's first contained in set 2, it must also be contained, because of this, it must also be contained in set 3, set 4, all the way up to set 999. And then we can see that this pattern continues all the way up to set 999. So depending on which set that the element first appears in, then we have all of these conditions. And since there are 1,000 total ways to choose the set that it first appears in, including the set that it does not appear in, then each element has 1,000 choices. So the answer is just 1,000 to the 999. Does that answer your question? Can I make a question that's based off of Felipe? Maybe. What's my favorite Pokemon? Snivy. All right. Okay, well, Gabriel, hopefully that answered your question. If not, you can always feel free to ask us on Remind or through the Flashmath class questions. And I'll actually be I'm gonna quickly repost these links in case people did not see them. So for resources, go to kidteachkid.org/flashmath resources. And if you want to ask questions after class, you can go to kidteachkid.org/flashmath class questions. I'm not sure if I'll make a question based off of Felipe. We'll see. And now we're going to be moving on to the next question, which is we're in the same boat. So pretty much it means that if set I, that means that if element I is not in set S, then element I plus 1 must be in set S, which is why it's kind of like, oh, we're in the same boat. Because what you do also affects me. And as usual, I'll give you guys some time to read the problem. What does E equal? Oh, E just means inside. So for example, so here this means that for all I that is in this set, so pretty much it means for all I, which is equal to 1, 2, 3, 4, all the way up to 9. Lazy outlining? Oh, come on. It wasn't that lazy. Okay, fine. If you guys really want me to outline it better. And I'll give you guys some time to think about it because people are complaining about my outlining apparently, but whatever. All right. Anyways, so now that you guys have hopefully had some time to read the problem, we're going to be starting. Let's see. Wait. So pretty much, we know that for any set 1, 2, 1, 2, all the way to 10. So for any I that is in 1 through 9, either I plus 1, or both must be in S. So as a result, we can start by constructing some smaller cases. So let's see. Huh? No, which? Oh, okay, never mind. So let's see. So for example, if we have if the element 1 is not in this set, then this means that the element 2 must be an S, because it says that either I or I plus 1 or both is an S. So if 1 is not in, so if this is not, then element 2 must be in. And from here, we can actually see that we can quickly do some strange sort of recursion. So for example, and I covered how to do recursion in one of my previous classes, so hopefully this makes some sense. So if we let f of n be the, oh wait, shoot, this is subsets. Oh, oops, I think I read the problem wrong. Wait a second, give me a second, guys. Uh-oh, we may be in a bit of a pickle here. Let's see. Okay, actually, I think I may have solved this problem incorrectly when I was doing it by myself, because I thought that this said sets, not subsets. So, oh wait, never mind. Oh, shoot, my bad. Never mind, I did read it correctly. All right, sorry, it doesn't matter. Subsets doesn't matter. Anyways, so we're going to be doing some sort of recursion. So for example, let f of n be the number of subsets of the numbers 1 to 1, 2, 3, all the way up to n. That satisfies the property that for all I, either I or I plus 1 or both is an S. So we can see that, let's do some cases on the first few elements, right? So for example, if element 1 is inside of S, if element 1, okay, let's see, right? So first, if element 1 is not inside of S, then we know that element 2 must be an S. So that means element 2 must be an S. So as a result, from here, we have the rest of the elements, which are just elements 3 through 10. And we want to find a number of ways to do this, still satisfying this property. So as a result, since there are 8 total elements in here, this is just equal to f of n minus 2. Now the other case is if 1 is inside. So if 1 is inside, then whether 2 is inside or not does not matter anymore. So for the rest of the n, oh, sorry, this is supposed to be n. So then for the rest of the elements, which are 2, 3, all the way through n, there are n minus 1 elements here, then there are just f of n minus 1 total other subsets that we can combine with it. So this is the recursion that we end up getting. Does that make sense? I know that was a bit strange. Anyone have any questions? Any questions? Any questions? Going once? Going twice? Okay. Oh, what? Yes? Oh, I'm in both. Okay, I don't see any questions, but you can feel free to ask. I'll come back to it later. What is that f? Oh, okay, so pretty much f of n represents the number of subsets. It represents number of subsets that satisfy conditions from the following set. Satisfy from the numbers 1 through n. So pretty much what we're trying to find is the value of f of 10. And this is like a common thing in recursions, which I covered a couple weeks ago, but don't worry. So yeah. So hopefully that answers. Are we going to do gen func? That's a bit hard. We'll see. Anyways, so now that we have this recursion, all we have to do is just find the smaller cases and then build up. So we know that f of 1 is just equal to 1. No, sorry, wait. F of 1 is just equal to 2, because it can either be the empty set or it can be 1. And then f of 2 is equal to 3, because it can either be 1 and 2, just 1, or just 2. And now from here, all we have to do is abuse our recursion to finish. So we can get that f of 3 is equal to f of 1 plus f of 2, which is equal to 5. F of 4 is equal to 8. F of 5 is equal to 13. We're going to be changing colors for no reason. F of 6 is equal to 21. F of 7 is equal to 34. F of 8 is equal to 35. Oh, sorry, 55. F of 9 is equal to 89. And lastly, f of 10 is equal to 144. So yay, this is our answer. And I actually managed to not screw up, despite thinking that I did actually screw up. So it's like a double reverse psychology sort of thing. So yeah. What is n again? Oh, okay. So this is just the recursion pattern that we have, and f of n just represents the number of subsets that satisfy the conditions given in the problem from the set 1, 2, all the way up to n. So for example, f of 10 would be the number that satisfies from 1 all the way up to 10. So any questions? Any questions? I know that might have been confusing, especially given the fact that I thought I messed up in the middle, but I didn't actually mess up, so. All right, so doesn't look like anyone has any questions. Oh, a question is a question. Yeah. Oh, I'm confused. What are you confused about? Which part? If it's just the whole thing, you can send us the question afterwards, after the class, at the link I sent, and then we'll do our best to re-explain it to you. Or, yeah, that's if you want us to re-explain the whole thing. But if you're just confused about a part, we can talk about it now. Oh, actually, it looks like it's 3:56. So I think now we're going to quickly review over some of the problems. I guess we don't have enough time to go over these last few problems, which are about the sums and differences and the fight to live. But if you guys really want to see the solutions, you can always ask us through the questions. But for now, if you guys have any questions about what we've previously covered, you can feel free to ask. So if you guys want me to go over any of these problems, just say it in the chat. If you want me to go over some of the introductory problems or explain something, then you can just say in the Q&A or the chat. So yeah. Why is the null set in f of 1? Oh, okay. So the reason the null set is in f of 1 is because it still satisfies. Because since there's no 2, so pretty much for f of 1, so as you can see, so when n is equal to 10, we want this property to satisfy for all I from 1 to 9. However, when we have n is equal to 1, we want this to satisfy from all, so pretty much, okay, so for f of 1, there's just no conditions really. So it's just any set. And the reason there's no conditions is because, yeah, because this number right here, 9, is 1 smaller than the biggest number. So 1 smaller than the biggest number here would be 0. So there's no really numbers between 1 to 0. So yeah. I hope that makes sense. Do Russians dolls again? Okay. Okay, let's see. All right, so pretty much what we're going to be doing is we're going to be doing casework over the first set that a number appears in. So let's look at the element 1. So let's say that 1 is inside of the set S1, right? However, we also know that S1 is inside set S2, and set S2 is inside of set S3, and so on. We know, and set 998 is inside of set 999. So as a result, because of this, since 1 is in set S1, S1 is in set S2, and so on, we know that 1 must be included in every set. However, now and we're doing casework on the first set that the element 1 appears in. So now let's say that the first set it appears in is set S2. So what this means is that it is not contained in set S1, and the first set it is contained in is set S2. So from here, we know that S2, since we know S2 is contained in S3, S3 is contained in S4, all the way up to S998 is contained in set S999. We know that we know that the element 1 will be contained in every single set from set 2 to set 999. And we can do this so on, right? We can see that if the first set is contained in a set 3, it will also be contained in every element up to set 999, and so on. And if the first set is contained in is just set 999, then the only set it will be contained in is set 999. However, it also has the option of not being contained in any set, so no set. And since there are 1,000 different choices here, because the element 1 can appear, the first set it appears in. Okay, so depending on the first set that the element 1 appears in, it's automatically determined whether or not the element appears in the rest of the sets. So for example, if we decide that the first set it appears in is set 997, then we automatically know it is not contained in the sets 1 through 996, and it must be contained in sets 997 and onward. So as a result, based on what the first set the element appears in, we know that whether or not it is contained or not in the rest of the sets is automatically known. So as a result, since there are 1,000 ways to choose the first set it is determined in, including the possibility that it is not contained in any set, then each element has 1,000 different possibilities. So as a result, the answer is just 1,000 to the 999. Yeah, I hope that made sense. Why doesn't f of 2 contain the empty set? Oh, the reason f of 2 doesn't contain the empty set is because here we want for all I that are in the set 1, 1. So for example, because let's say that the element 1 is not inside of the subset, right? Well, in this case, we know that the element 1 plus 1 must be in the set S. So that's why it must be in. So like if we have the set, so for f of 2, let's say we're trying to build a subset, right? So if we know that 1 is not in here, then because either I or I plus 1 must be in S, we know that 2 must be in here. However, the reason we include the empty set for f of 1 is because even if 1 does not appear in here, there is no 2. So this condition doesn't really matter. So that's why the empty set appears in f of 1, but not f of 2. I hope that made sense. Yeah. But okay, yeah. So now it's 4:01. So hopefully that all made sense. I hope you guys really enjoyed our classes today for number theory and combinatorics. I know that I sent out the invitation a bit late, so thanks you guys all for coming. And don't forget to attend Isabella and Andy's class tomorrow, which will take place from 2 to 4. And I heard that they're coming up with some pretty interesting stuff. If you guys have any questions, feel free to ask at kidteachkid/flashmath class questions. I'll put the link in the chat again. And yeah, so bye guys. You guys can leave now.